This video is on oxidation reduction reactions. We looked at oxidation reduction reactions in chapter 5, and now we're going to look at them again and how they pertain to organic substances. So anytime you see an oxidation reduction reaction, it has to do with an energy transfer. As one reactant loses electrons, which is oxidation, another reactant gains those electrons, and that is reduction. And we had some memory triggers to help us with that. We had oil rig and Leo goes Gur, where loss of electrons, Le, is oxidation, gain of electrons is reduction, and same thing with the oil rig one. When we look at organic substances, it's going to be harder to track the electrons because there's so many more atoms than electrons, but we can look at oxygen and hydrogen atoms. In an oxidation part of the reaction, you will see an increase in oxygen atoms and or a decrease in hydrogen atoms. I like to think of this that in oxidation, your O's increase. O in oxidation, O increase. And your H's just do the opposite. And then with reduction, as you might imagine, it would be reversed. Your oxygens would go down and your hydrogen atoms would increase. So that's really what we're going to look at more with organic substances, what's happening to the O's and the H's. An oxidizing agent is a reactant that is reduced, and it causes the organic compound to undergo oxidation. So here's an example where you will see ethanol being oxidized to ethanol. So if you look at your H's here, you have 6 H's in ethanol, and in ethanol you have 4 H's. So since your H's went down, you know that that was oxidation. This O in brackets right here means that there is an oxidizing agent there. And your oxidizing agent, again, gets reduced. So because we know that is reduced, we already would know that this would get oxidized, because if you have one, you have to have the other as well. On the flip side, reducing agents is a reactant that is oxidized and causes the organic compound to undergo reduction. So this H here, this means reducing agent. And you can see what happened with your H's here. Your H's went up, which means that this got reduced. And then your reducing agent got oxidized. So look at your H's or your O's. In this case, these two cases was H's, and see if they're going up or down. If you're looking at your hydrocarbons, starting at the top here, you have an alkane. As you're going down, this is your oxidation pathway. An alkane gets oxidized to an alkene, which gets oxidized to an alkyne. And again, with oxidation, your O's are increasing, your H's are decreasing. So look at your H's. As you're getting oxidized, your H's are going down. So it is very common that an alkane will be oxidized to an alkene. And then reduction obviously would just be the backward effect, going up this way. An alkyne would be reduced to an alkene, which would be reduced to an alkane. Here's something called catalytic hydrogenation. And this occurs when your alkenes, your carbon-carbon double bonds, react with hydrogen in the presence of some kind of metal catalyst. So palladium, platinum, nickel, etc. It reacts with those to form an alkane. And again, if you're going from an alkene to an alkane, you are being reduced. So here it says, write the Lewis structure of the product formed in the following reactions. So look at what we're starting with here. We're starting with this compound, and we have an H up there. So that H, if you remember, if there's an H on the arrow, that is a reducing agent. So that thing, whatever that is getting oxidized, which means your organic compound is getting reduced. So what's going to happen here is this double bond, we're always looking for the double bond or something like that, that is going to form an alkane. It's going to go from alkene to alkane because it's being reduced. So you are going to add H's. So this is being reduced, which means add H's. Alkene to alkane. So a bunch of different things going on here when something's reduced. So these C's, my end C circled there, will now have 3 H's on it, because it's now all single bonds. And that will single bond to that C, which will add another H on that as well. And then the rest of the molecule will be the same over here. And you can see what that looks like here. For the second example here, okay, we have our H2, and just happens to be our platinum here. And look, we have our alkenes. And it gives us a hint here. It says the carboxylic acid functional group is unchanged. So that's right here. That's not going to change. The double bond, the alkenes, is what's going to change here. And that's going to go to an alkane. So that double bond will go away. And then instead of this C, which currently has 1 H, and this C, which has 1 H, and this C, which has 1, they will now have 2 H's. That will become an alkane. So you can see the C's, which were here and here, I believe. So what was a double bond there, notice now goes away. Okay, and we know that because of our H there, which again tells us that's our reducing agent. So we know the organic compound gets oxidized. And then we have our H2 here, which is our catalytic hydrogenation. Here's an important chart that I would encourage you to write down somewhere. So if we're following our arrows here, I'll just look at the oxidation pathway going down. If you have a primary alcohol denoted by our OH and our C is only bonded to one R group, that will get oxidized to an aldehyde. Remember your formula for an aldehyde here. Your C is bonded to an H and then an R group. And then your aldehyde can get oxidized to a carboxylic acid. So every time we're getting oxidized, we're losing H's or gaining O's or something like that. But if you see a primary alcohol and it gets oxidized, it's going to turn to an aldehyde. Moving along, if you have a secondary alcohol, that will get oxidized, again going down here, to a ketone. And then if you have a tertiary alcohol, there is no reaction to that. There is no H's to be lost off this carbon. Notice they're all R groups. So that will be a no reaction. We'll have a question like that coming up. And then, of course, if you're going to talk in terms of reduction, you would just reverse all of these. The carboxylic acid would be reduced to an aldehyde, which would be reduced to a primary alcohol. This is actually how breathalyzer tests work, oxidation reduction reactions. So what happens here is ethanol, the alcohol, is oxidized to ethanol. And then that is oxidized to ethanoic acid. So we have our primary alcohol. Then we have our aldehyde. And then we have our carboxylic acid. And that's what we just looked at on the other page. That's the chart. The oxidizing agent is something called chromium 6. Chromium 6 is Cr plus 6. And that is reduced, or that gains 3 electrons. So if it gains 3 negatives, it is now Cr plus 3. And then this concentration is determined by the shade of green. And that can tell you how much alcohol a person has on their breath. So that's pretty cool. That's how the breathalyzers work. Okay, here it says, predict the structure of the product formed in the following reactions. If no reaction occurs, indicate why. So again, our first one here, we have our H on top. And that H on top, this means it's a reducing agent. So that got oxidized, which means this guy is going to get reduced. It's going to gain H's. So we are going to look right at our O double bond C here. If you notice, this current structure is a ketone. It's O double bond C to 2 R groups. A ketone will be reduced to a secondary alcohol. And if you look here, a ketone moving up will be reduced to a secondary alcohol. So it is going to gain an H there. So what that will look like, I think it's on the next page here. Look what happened right here. That your carbon down low gained an H. It's single bonded to the oxygen up top. And then that oxygen gained an H to become an alcohol. Remember, to be an alcohol, you need an OH group. And the reason it's a secondary alcohol is because that C is bonded to 2 R groups. For B here. So B, look at what we currently have. This would be a primary alcohol. And notice what we have on top here. We have an oxidizing agent, meaning this will be reduced, meaning our reactant here will be oxidized. So if it is oxidized, it's going to lose H's. If you remember from the chart, your primary alcohol is oxidized to an aldehyde. So we are expecting an aldehyde on the right-hand side here. So if we see what happens, these are flipped around, but I will highlight here. Notice your alcohol, your C to your OH group, that alcohol goes away, and you have your C double bond O to an H, and then your R group here. So remember, an aldehyde is O double bond C R H. So that's exactly what we have here. And letter C here, we have an OH bonded to a C right here, and this C has 3 R groups. that means this is a tertiary alcohol. And since it's an O on top, that means this is going to be oxidized. What is a tertiary alcohol oxidized to? If you remember from our chart, there is no reaction for that. Tertiary alcohol cannot be oxidized. There's no H's to be lost. So letter C there, it should be a no reaction. Okay, coenzymes. So in biochemical pathways, coenzymes are oxidizing and reducing agents required by some enzymes which are not changed during a reaction. So we have a mouthful here. It's called oxidoreductase. That's this word right here. Oxidoreductase. And this is a class of enzymes that catalyze oxidation reduction reactions. Two really important coenzymes we're going to look at. This is the first one here. So this is NAD plus and NADH. So they stand, this is an acronym, I'll show you on the next slide. NAD plus and NADH are used as coenzymes with carbon-oxygen double bonds. That's when they are used. So we want to focus in the blue square that's highlighted up here. And I want you to look at the nitrogen atom. And I want you to look at this H over here. So what happened is that our NAD plus is reduced to NADH. So NAD plus is on the left, NADH is on the right. So it gained an H, right? It went from NAD to NADH. It gained an H. When you gain H's, that is reduced. You can look at your H right here that was gained from it. So your oxidized form is your NAD plus. This is your oxidized form. If you would go in reverse, right, they're both here, depending which way you go. And then your reduced form is NADH. You can see that the nitrogen had a positive charge here with 4 bonds coming from it, a double and 2 singles. And then over here, it only has 3 bonds with a lone pair on it. So here is what it stands for. And again, that is when we see carbon to oxygen double bonds. Here is an example of it. So this is ethanol going to acetaldehyde right here. And then that's going to acetic acid. So your ethanol, that is our primary alcohol, as we can see right here. Your acetaldehyde is your aldehyde. And then your acetic acid would be your carboxylic acid. And again, that comes from that flow chart on the other slide. These are being oxidized. So when you're going this way, that is oxidized. It was the down arrow in that chart. Your NAD right here, that's gaining an H, right? So that is being reduced. And remember, if you already have one being oxidized, the other thing has to be reduced. You can see what happened structurally with them that your OH group here turned to your carbonyl carbon with an H and an R group. And then you can see your carbonyl carbon here has an R and an OH group. And that's the carboxylic acid skeleton. Your other coenzyme that we're going to talk about is FAD-FADH2. These coenzyme involving carbon-to-carbon double bonds. So the NAD plus and NADH was the carbon to oxygen double bonds. This is your carbon-to-carbon double bonds. Your FAD down here gets reduced to FADH2. Again, it's gaining H's down there, which would mean the organic substance itself is going to be oxidized. So that is what the FAD stands for. And again, it's carbon-carbon double bonds. So right here, that is being reduced. And here, if you look at the two different structures, the middle portion is what's different here. On the left, you have those carbons with 4 H's, and on the right, you have carbons with 2 H's. So you lost H's there. You lost H, which means it's oxidized. If you remember from one of the previous slides, your alkane turns to an alkene through oxidation. So on the left, notice we have an alkane here, all single bonds, and on the right here, we have our alkene, our carbon-carbon double bond. For the oxidation reduction reaction shown below, determine whether the substrate and the coenzymes have undergone oxidation or reduction. So let's look at A first. I'll draw a line there. Acetaldehyde, that is our aldehyde, and it's turning into a carboxylic acid. So we know because of that that is oxidation. Oxidation, you lose H's. Look what's happening to our C. There it has 1 H. Here it has no H's. It's bonded to 2 O's and a C. Your enzymes here, that gained an H, so that is undergoing reduction. And there's your answer. And for B here, can start with the enzymes. Your FAD gained H's, so it got reduced. And what I would look at for these structures here is I have an alkane here, and now notice I have a double bond right here. I have an alkene. So if I'm going alkane to alkene, that is has been reduced. Or sorry, that has been oxidized. That has been oxidized. It lost, another way you could look at it, it lost H's. So if we're looking at this carbon right here, this carbon has 2 H's, right? It would have an H here and an H here. And this carbon at the bottom, since it already has 3 bonds, that would only have 1 H. So it lost 1 H. So that was oxidized. And there is the answer.